Welcome to a special 15-year anniversary episode of Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today it's my pleasure to welcome Leonardo Spanu, Senior Researcher in R&D Chemistry at Shell Corporation, where he is part of the New Energy Research and Technologies team. Leonardo, thank you so much for joining us today. Can you tell us a little bit about yourself and how you first got involved in nanotechnology?
Yes, so I have a PhD in physics in condensed matter, and I joined Shell about 7 years ago, moving from University of California. Some of my early projects in Shell were mostly focused on understanding active phases of catalysts developed at Shell, and by a combination of simulation, testing, and characterization. Now, the chemical industry, the refinery industry have been using nanotechnology for almost centuries without actually knowing it. A lot of active phase in catalysts are actually at the nanoscale. So one of my early projects in Shell were actually trying to understand this great challenge of connection between morphology, performance, synthesis. So in a way, Shell and also other chemical and oil and gas company have been exposed to nanotechnology for a long time and designing materials that eventually turn out to be nanomaterials. More recently, in the past 3 years, actually, I focused some of my research activity on nanotechnology on purpose. So I'm part of a team which is called New Energy Research and Technology, and we are looking at novel solutions for energy. And there, nanotechnology may play a prominent role by design from the beginning.
Nanotechnology on purpose is a great phrase. I like that. So you mentioned that you're using nanotechnology in a variety of ways. Can you share a little bit how you're using it in New Energy Research and Technology Group?
So the New Energy Research and Technology team is a relatively young team in Shell. And basically, our main mission is to explore and develop technology for provide energy, fuels, chemical with lower carbon footprint. Royal Dutch Shell has made a very important commitment to lower our overall carbon footprint. So we have a broad portfolio including solar, wind, storage. There are 3 areas in particular where we are focusing, and we believe novel material based on nanotechnology may play a role. One is definitely advanced energy storage, so how we can storage some of the energy that is being produced, for instance, via renewable energy. Another critical area is how to capture, for instance, CO2 from air and convert it possibly in fuels and chemicals. In particular, my research area is methane to products, so converting natural gas, methane in particular, into chemicals and materials.
So can you share how nanotechnology plays a role in that conversion of methane to other chemicals and materials?
Yes, so there are multiple aspects where we believe nanotechnologies may play a role. On one hand, we have what I would call the more traditional side, so designing catalysts that could be selective, possibly creating new chemicals and product, again, with an overall lower CO2 footprint in the conversion process. But also, another area of interest is actually converting the gas itself into nanomaterial, for instance, carbon nanomaterials that could be then used into materials at scale. So in some way, both the process and the final product could leverage some of the knowledge that has been developed in the past 15 years in the broader nanotechnology community.
What are some of the challenges that you face in the research that you're doing and taking them into technologies that are commercially viable?
I think one of I would call it the biggest challenge is to translate property proven at the nanoscale to kiloton, megatons. So how do we translate a discovery from the bench scale into something that could work commercially at large scale? That's, in my view, that's the greatest challenge we as a team we are facing. And I think probably we share this challenge with other teams across industry and also in academia.
We often hear that that's a big challenge. I'll take the shorthand and say Scaleup is a really critical challenge facing the commercialization of nanotechnology. We use what we call the technology development pathways framework for looking at how research works through the development cycle into commerce eventually, and have drilled down through workshops and in other events at different steps along that technology development pathway where there's critical challenges like scale up. Another area that we hear is the in situ quality control, the monitoring tools in order to do that. Are there other steps along your technology development pathway that you see there are critical needs for research to address?
In some way, you have mentioned together with Scaleup, we have to develop standards for materials. Because once we have developed standards, we can enforce quality control and consistency at scale. A lot of materials, and I keep referring to the nanomaterial, for instance, carbon nanomaterials, because it's an area where I'm more familiar. Sometimes they are produced in a semi-batch or batch mode. And it's not uncommon to purchase materials from the same vendors with different properties. In the broader chemical industry, when you purchase a specific chemicals from a vendor, you know 100% what you are buying, the amount of impurities, the specs are well defined. I feel in certain area of the nanotechnology, we haven't developed sufficient specification for the material. Therefore, it's also hard to implement a specific technology on a product because over time, the performance may change.
I want to switch gears a little bit and talk about interdisciplinarity. What intersections have you had in the team that you work with, working with nanotechnology?
I'll give you an example of a possible concept that could help actually decarbonize the energy sector and utilize, for instance, natural gas, especially here in the US. It's this concept of moving from natural gas and converting the natural gas into hydrogen and materials. So, for instance, you can start from methane and produce specific form of carbon nanotubes could be assembled into fibers. The fibers eventually will go into a composite and then in a automotive or aerospace components. Now, we have been exploring this option, and in our team, we have people from at least 6 or 7 different backgrounds. You need someone who is able to understand, for instance, the nanomaterials, what we call the carbon intermediates at the nanoscale. So typical material scientist. We need someone who is working with composites, so with the end user on how to place this material into a fungible product. We need traditional engineers with an expertise in reactor design, a team who is able to characterize this material at the nanoscale, possibly also in situ during the synthesis conditions, and possibly also folks who are more related to, let's say, the renewable side, let's say an electrical engineer, how to bring the renewable energy into a process in such a way that the overall carbon footprint will be as low as possible. So in some way, although, for instance, nanotube has been now as a 25 years topic, when you want to bring it at scale, when you want to create a commercial process that could actually generate value, you really need, working with an interdisciplinary team is almost like a must. You cannot escape having several expertise in the same team, in the same room.
So, as you know, the NNI is celebrating 15 years since the 21st Century Nanotechnology Research and Development Act was signed into law. And we're reflecting on what both scientific and technological and commercial activities have advanced over that 15 years. From your perspective, could you share some of the nanotechnology advancements that you've been interested in?
Yeah, I confess there are plenty of discoveries or work that kept me very excited and motivated in the past 10 years. However, I want to point out to a specific case, but I want to emphasize, in my view, the greatest contribution of nanotechnology or all the work that has been done, especially in the United States, is to push the boundaries of characterization tools and techniques. So the moment you have to understand a new class of materials at the nanoscale, you are forced, as a research team, as a scientist, to develop new tools on how to look at your experiment, at your materials, or what you are doing at the lab. And obviously, the moment this class of tools are developed, then they can apply it also in other fields. So right now, to me, it's always amazing what we can do with in situ characterization and the ability of characterize and understanding, for instance, reactions or synthesis mechanisms as they happen. Another area is blending together the synthesis part, the characterization part, and also the atomistic simulation. This has been, in my opinion, a great achievement, and it has been possible because there was this broader community working, yes, on different topics, but united by the need of understanding how atoms, how molecules arrange together at the nanoscale.
I know that you've mentioned a number of the research projects that you're working on and where you see nanotechnology playing a role from the perspective of an energy company. But looking broadly, or perhaps narrowly, either way is fine, what are you excited about with respect to the potential for nanotechnology to address challenges in the future?
Well, I may be biased and maybe I'm repeating myself, but for scientists of my generation, I truly believe the energy challenge is the challenge we have to face. So how do we provide energy with a lower carbon footprint to a growing world population? That's where I feel nanotechnology may be and could be actually a great enabler. I cannot point to a single field where I think nanotechnology will solve all of our problems. The way I see the future is we will have to attack the energy problem from many angles. So we will have to build a portfolio of solutions. And maybe each of these solutions will change depending on geography, depending on the population or the specific environment where the technology solution has to be deployed. In fields like CO2 capture, CO2 conversion into fuel and chemicals, conversion of natural gas into valuable product, energy storage, there are three critical areas that if we make progress, we can actually have a positive impact on the overall energy system. And in all three cases, mastering and understanding how to deploy nanotechnology at scale will be crucial.
I would first like to really thank you again for your time today and ask you if you have any closing thoughts for the listeners.
I'm going to repeat myself, but it's a message that I want to pass maybe to younger students or people who are entering this field. Keep exploring the nano world, but always think about the biggest picture. So I think there is a great value in trying to understand where your new nanomaterials, nano device will fit, how you can deploy that, how can these new nanomaterials can be embedded in maybe non-existing product, or how you can really make sure that people will leverage or utilize this new piece of science. So in the past 15 years, we have seen amazing science, and I truly believe that now is the moment to see it applied at scale to actually tackle critical problems like energy and the energy transition.
Thank you for joining us today for this special 15-year anniversary edition of Stories from the NNI. If you would like to learn more about nanotechnology, please visit nano.gov or email us at info@nnco.nano.gov and check back here for more stories.